Welcome to this introduction to pcb-rnd. If you're here, you probably already know it, but just to be sure, I'll still say it. pcb-rnd is an EDA software for printed circuit board layout, as the name might have suggested it. It is free and it is available on all major platforms. But why would you use it? Is it because it's very lightweight, blazing fast, or doesn't require an internet connection? Well, that too. But for me, it's like when I switched from Notepad to Vim or Emacs. It's meant for power users. But for now, let's just get started with it. But if I go too fast, just rewind or decrease the playback speed. Starting pcb-rnd reveals an austere interface from the last century. But no worries, it is still very functional and actively being developed on. By the way, here I'll be using pcb-rnd 3.0.0. Later version might differ in details, but the same basic concepts still apply. Like most EDA tools, you find layers, menu, tools, and a status bar. We will mostly use surface mount devices in this demo. And because most of them are metric, I will switch the grid unit from inches to millimeter by clicking on the top right. You can also use the menu. View, grid, grid unit, millimeter. You see the corresponding shortcut, GM for millimeter and GI for inches. Most actions have a shortcut, and as a power user they will become very handy once you learn them. And pcb-rnd allows you to freely define them or even create new entries in the menus. But for now, let's just try it. GI for inches, GM to go back to millimeter. And on the bottom of the screen, you see your last keystrokes. Let's also switch to a coarse grid for part placement. Go to View, Grid, Grid Units, Grid Size, and go to 0.5 millimeter. You can also see that you can switch the grid size with previous grid and next grid, GB and GF. So let's use 0.5 millimeter, and you can see on the bottom right, the grid is 0.5 millimeter. Now if we press GB, we go to a finer grid, which is 0.25 millimeter. And GF, we go back to a coarse grid, 0.5 millimeter. Next is setting up the board. In the preferences, let's set the name. File, Preferences, Board Meta, the name. This will just be a demo. And if we switch to the Layer tab, we can actually see the board stack up. We don't need the internal layers, so we will remove this group and remove this group. So let's close it. And don't forget to save the progress from time to time so you don't lose everything. File, Save Layout. And let's save the layout into demo.lht. Now you could start placing components. Here you can find the library, and there you can find some of the most basic components. If we open it, we find SMD, most common SMD like 0603, and then we can place them. We can also find parametric components, like for example on this connector, which is a through-hole connector. And this is parametric, so we can change the number of points and so on. So let's open the GUI for the parameters, and let's have a 2x5 connector. We can even make some other changes or leave it just by default. And here we have a 2x5 connector. But there you can only find the most basic footprints. This is fine because there can be no exhaustive, perfect library of footprints. You always prefer to use your own collection of footprints, which matches your needs and preferences, and mostly, which are proven and trusted. Luckily, pcb-rnd supports most common footprint file formats. And to import them, you just go to File, Import, Load Subcircuit to Paste Buffer. In pcb-rnd, footprints are called subcircuits. Some manufacturers provide footprints in BXL files, like this one. If you select it, it will not place it directly, but put it in the paste buffer. This is why it is red. The paste buffer allows you to work on the footprints, but most of the time we just want to place it by clicking on a position. And voila! To clear the paste buffer, just press Escape. If you're coming from another EDA tool like KiCad and you already built your library, then you can just import the KiCad footprints. File, Import Subcircuits, pcb-rnd, KiCad, and let's just open this footprint and place it. Now when your window popped in, This is the message log, and it will become a very important friend. This is where the program will show you warnings of or errors. Warnings are in red, errors are in blue. And here, while opening the footprint and placing it, it found out that some pads don't have any clearance which are defined. So it uses a default value. Once we've acknowledged it, we can clear it, and here we are. But often before you do the board layout, you already drew a schematic. This will be our schematic. I will not explain it because it is outside of the scope of this video, but here is a link for more information about it. PCB is only for board layout. For the schematic, you will have to use another EDA software. This was Lepton EDA, but it doesn't really matter. What is important is that in the schematic, I already specified the footprints to be used for the parts, and pcb-rnd can automatically import them. You just have to tell it where to find them. For that, go to File, Preferences, Library. And this is where it goes through when looking for footprints. There are already some default paths, but we want to add one for our subsequent folder, which holds my footprints. So click on Insert Before, and then you can have a small help with some variables which help you define the path and sometimes relative paths. For example, we will use RC path design, which corresponds to the folder where our file is stored in. So let's type rc.path.design, and you see that it already expands it, but we will just keep the variables. So this allows us to move the file and always have the folder relative to the file. And my footprints are in the subc directory, like subcircuits. We press OK. Now we have it there. This is done. So we are now ready to import the schematic. Let's first remove the footprints because these are not part of my schematic. For that, just hover over it and press delete. And just before I import the schematic, I want to add a layer. So this is the layer stack up. Most common things are the top solder paste, then the top seal screen where you do put your text and so on, top solder mask, which removes the mask so you can solder on the pads. Then we have the top copper, and these are actually on the left you have layer groups, and within layer groups you can have multiple layers, and this allows you to have different colors for different signals. It makes it a bit more readable with time. After the top copper we have bottom copper, bottom solder mask, bottom seal screen, and bottom solder paste. And then we have other kind of less usual but still very important layers. The global outline, so the board outline, slot plated and unplated. These are if you want to have long lines or cutouts which are either plated or unplated. Then top and bottom assembly, fabrication, and these are all virtual layers, not important for now, we'll see that a bit later. What I do want though, which is not here, is create a new group, and here we can see we have different type of group layers. I want to have the keep outs, and for the keep out I only want copper top side for components to not be close to each other. So this is the keep outs, and we've seen that it added a group, and then within the group also a layer, top layer KO, like keep out. Now we are ready to import the schematic. For that, go to File, Import, Import Schematic. And since PCB-rnd doesn't come with a schematic capture software, it allows you to import the raw schematic, the source schematic, from a lot of different EDA tools for which you can use to draw the schematics. In our case, I use Lepton, so let's browse to PCB-rnd, and this is the source schematic we will be using. And if I click on it and click on import, and imported everything, but you don't see it directly because the new parts are placed outside of the current drawing area of the board. And we see already here the keep out is enabled. So in my footprints, what I do have is some keep out area which tells where the part could be. And it is important that two components or two parts or two footprints doesn't overlap on the keep out, because the pick and place machine could have issues placing the two together. Most of the time I don't want to see it, so I can switch it off by clicking on the square here. Same thing, you could remove the top seal screen or any kind of other layer. Just turn on and off the visibility. Now, the import worked for all the parts. The next thing which we need from the schematic are which pin is connected to which other pin. These are the nets, and we can have a look at the nest by looking at rat's nest and then OptiRats and rat's nest, or CR, and here it displays which pad goes to which other pad. So you see the orange lines, and this is where we see the virtual parts. These lines are just also on a virtual layer. You can even select them and remove them, but it doesn't remove the net in the back. We still know, the program still know that this pin needs to connect it to the other, and we can see it with CR, so optimize the rats, and we can still see the shortest route between the two pads is this one. If you want to erase it because you don't want to see them, you can just erase all of them, or you can just disable this virtual layer. Importing a schematic to work flawlessly, we have all the information for laying out the board. But what if pcb-rnd doesn't support your schematic capture software? Then what you can do is every schematic capture software allows you to export a so-called netlist, and the netlist includes which parts and which pins within the part are connected to each other. And you can see pcb-rnd supports a lot of different netlist formats. So with that, you can use any schematic capture software just for the schematic, or any EDA tool just for the schematic, and then switch to pcb-rnd to do some board layout. You should have no issue with that. Next part is here. In my footprint, we have reference designators. So J2 and so on identifies that this part is called J2. This is useful when you want to assemble the boards. Then you know that the part defined by J2 should be placed here, and this is the footprint. I don't want it to be on the top silk. So for now, you can see that this is on the top silk. If I disable it, they are removed. I want them to be in my assembly layer. So very often they're in the top silk because you make them on the board. My board will be tiny and I don't have a lot of space, so I don't want to put them on the board. Also, it will be automatic assembly. It's meant for assembly line, nor pick and hand picking. We could still do it, but we don't want. So if we look at top assembly, well, I enabled it, we see that we have other text which are already there, and these are the names of the connectors. I don't want them, so I will remove them. Just hover over it and press delete, and I remove the name of the component, which is in this footprint actually, and it could be useful for you. In my case, it is not. And what I want to do is now put all the reference designators in the assembly layer. So I can select them by clicking on them, and then you can see that they are highlighted in turquoise, and pressing shift and clicking on the other reference designators, I select multiple of them, up, up, up. Now I selected all of them, and to put them in the top assembly, I select the top assembly layer, and then I go to select, move selected objects to current layer. This is how you can also move complete circuits to the subside. For example, if you have parts on the top and the bottom, the same way you would select the complete part and then say move selected subcircuit to the other side. So if it's on the top, it will be on the bottom and so on. For now, we will just put it in this top assembly layer, and as we can see, it is not there anymore. Now we can start with the board placement, and routing a board is a very iterative process. We will fine-tune it as long as we go, but let's start with the placement. To move objects, you just directly press and drag it by clicking using this arrow selection tool. You don't have to select it. You can already immediately drag it. Same for the reference designators. You can just move them, and we move them around because we will just select the part afterwards, and we don't want the reference designator to be in the way. So up, reference designators, out of the way. The other important part is rotating the parts. This is this tool here, rotate an object. And these tools here, or these functions, are actually mapped to the function keys. For example, if I press F1, it will select the via function, F2 the line function, and so on. And what I need now is the rotate function. This is F9, and you will quickly get used to these F function keys and don't want to drag the mouse all the time there. It's a lot faster to switch tools using the function keys, and I recommend learning them. They will arrive really fast. So this will go this way. I'll move these parts this way, and if I press escape, I deselect the tool and go back to the default one, which is the arrow, and the arrow allows me to move the parts. There we have it. We have our first placement. I'll fine-tune it as long as I go with the routing, but for now we do have the rough placement, and we do have everything we need. So now the rough placement is done. Another tool which is important, or another trick which is important, is actually looking at the rat's nest, because it will indicate if a part is well placed or not. For example, this will connect here. It's probably not the best way to have it sneak around here. This part is connected here, so it's a good place. This one connected here, and this pin connected here, not very good. So we can actually optimize it, turn it 2 times around, and then we can see that this rat's nest, or this connection, is a lot better. I'll probably not do it because I like how the silk screen on all the LEDs are done, but you could do it this way and it helps a lot. Now, if you only want to see not all the rat's nests, so let's remove them, but only the one which are connected here. Select the components, go to connect rat's nest, and then address to selected pins. And it only puts the rats to the selected pin. If I go to something like this part, which is a coin cell battery holder, and then add rat's net to selected pin, we see that it puts not only the connection directly from this pin to the other, but also what the other connected. For example, these are connected all together, and it added the rat's nest for that. And you can erase them, or you can select, or you can just select individuals one and erase them. So this is useful for placement and having a rough indication. Now let's go to the routing part, and this is this screen here on the bottom left, which I didn't explain yet. These are the route styles, and here are the tools to draw the routes. So the tracks on the top copper, so you have to select the top copper, we have to select one of the layers. I will do in the signal layer within the top copper group. And then I can draw traces up to there. Escape to stop drawing a trace. And now if I do the rat's nest again, you see that this one has been removed because pcb-rnd knows they are connected together. If you want to draw on the bottom layer, just select bottom layer, and then you can draw on the bottom layer, and you can see it uses the color which are all also defined here, which you can actually change. For now, we just want the top, and to select the top really fast, just press on 1. 2 is for bottom, 1 on top. You can configure it. These are by default the values, and most of the time they're good enough. Now the trace here has a width and then has a clearance. These are defined in the route styles, which I haven't explained yet. And you can have 4 or more route styles because you can add new ones. But the route styles, if we click on edit, this is where we define them. This is the name, and this is the line thickness. I find this line a bit thick, so I will use something like 6 mils because most PCB manufacturers support 6 mils. It is a very low thickness, and it allows me to sneak between pads. We could have something larger. In my case, for signals, it is good enough. I don't need anything larger, but you could add anything larger. And then the clearance between the traces is also often 6 mils. You can define the unit actually, say in millimeters. I've defined in mils. And if I close it and now draw a new line from here to here, you see that the line is a lot thinner. It is now just 6 mils. This is what you see here also. Here the line is 0.15 millimeters. These are 6 mils. And the clearance is also 6 mils. If you want to draw their For example, let's go here. When you draw, it first tries to do a straight line and then a diagonal line. You can change it temporarily by pressing on Shift. So it first tries to do the diagonal and then the straight line. This depends on how you want to route it. Shift is just temporary though. What you can do is when you go to Mode, Routing, here, I think it's Cycle, here, this one, Cycle Line Clip Refraction, MLF, or the hotkey is /. If you click on it, you see that the style here on the bottom changes and it indicates in which mode you are. Here it starts with a diagonal and then a line. This is what we see here, diagonal and then a line. If we press Shift and then line, we have an X. X is only straight lines, and then we are back to straight line and then a diagonal. Well, horizontal or vertical line and then a diagonal line. This is how we switch between line styles. And you can also have arcs, or you can have any kind of degrees, but these are 45 degrees line are the most common ones. Now the next important part for drawing is the vias, which is this tool here. When we place a via, it allows us to connect one side of the board to the other side, so the top to the bottom side. And now we can put a trace to this pin, go to the bottom by selecting this layer or pressing 2. Then we can go up to here, press F1 for the via, F2 for the line, go to the top line, and then we have a trace going here. This way we connected this pad using 2 vias up to here. Now this is the wrong path. I just drew it fast to show it. And we can actually see it if I press CR. You see that the message log has already shown again, and it tells us that there is a short. This is not what it's supposed to be, and where there's a short, it also puts the pad in very flashy orange, and it tells you, there's an issue here. But this is just for the demo. At least this is how you can see if you route it wrong. Now, the vias here are super large. These are the default one. To change the shape of the via, you again go to the route styles, edit this route style, and this is what you see here, via pad stack. So a pad stack is how pads and pins are defined. The via here is defined using a pad stack. This hole here is defined using a pad stack. Just holes are defined pad stack. This pad here is also a pad stack. So it's everything which you find with a hole or with a copper plane is a pad stack. Traces are not pad stack though. But here we want to change the pad stack. So let's click on the pad stack. We have an overview and we want to edit it. So let's edit the pad stack. These are the definition of the pad stack. Let's ignore it for now because we want to make a new pad stack. So the shape is a circle because the vias are very often circles. We will have 0.8 millimeter would be the complete via, so hole plus the ring. And then the drill size will be 0.4 millimeter. Most of the manufacturers support these dimensions. And then you can generate on which of the layers it generates the form. If we want exposed top and bottom copper, this means do we want that the ring is exposed so we can access it. This is called an untented via. I don't want it. I want tented vias. I want solder mask on top of the copper. I don't want to have solder paste on top of it, so I will not enable this one. If we click generate, we already see that it changed this form. It changed the pad stacks here, and the prototype change. We see what we've defined. On the top, the bottom, and in any of the internal layers, we have a 0.8 millimeter circle. It could be any other shape. It could be a rectangle, it could be a hexagon, it could be just a trace or a line. And this makes pad stack very powerful because any kind of shape can be used as pad stack, meaning any kind of shape can be used for pins and pads and for vias. Then we have here the hole diameter, and then we want this hole to be plated because it will be a via connecting the top copper to the bottom copper. But for example, if I want something a bit more complicated, I want it to be tented on the bottom, but untented on the top. So on the top mask, I will say derive automatically, and yeah, Here we have the preview. On the preview you can see in red that on the top the solder mask has been removed, and now this is untented but just on the top. In the same fashion you could use also another shape than just a circle on the top. You can do the same thing on the bottom and so on. So it makes it very powerful. So let's remove it because I don't want it. So delete, there will be no shape, close, and I'm pretty happy with the shape. You selected, close, and then if we press via and now put the vias, they are all small. And again, here you can easily find out what is a pad stack, what is not a pad stack. If you go to the virtual layer and press pad stack, I don't want to show them, it will remove them. There are still holes here, so you can say I don't want to see the holes because for my routing it's not important now. You can remove all the holes. You can remove all the sub-secrets, which are, but these red bounding box, this is just to tell where the sub-secret is. It's nothing which will be in the end fabrication file. And this is how we place and how we route all the signals. And with that, we are actually ready to route everything. We have all the tools we require. So let's do some routing. One thing I haven't shown yet are the polygons. And whenever you want to fill a copper area, for example, if you want a ground plane or any kind of plane, you use the polygon tool, which is like polygon or rectangle. Here I've used the rectangle tool and we are still on the top signal. I will change it and put it at top ground because this will be a ground plane. And you just draw the polygon. For now, the rectangle, for now it will be imprecise, but we will tune it later. This is just a rough drawing. Here we now have a complete copper plane. Now you want to connect some pads to this copper plane, and there are several ways to do it, but the easiest way is using the thermal tool, which is on the top. So click on thermal, and then all the pads you want to be connected to the copper plane, you just click on the pad. For example, this will be the minus from the battery. So this will define actually the ground. So let's click here and you see that it creates thermals around this pad. So now this is connected to this copper plane, and actually if I do CR, you see that this is this pad, which should also be connected to minus here. They now indicated please connect it to the nearest object, which is ground, which is this copper plane. If you don't like this style of thermal, just press Shift and continue clicking until you find one. And this is how you do ground plane, or you use rectangles and you use shapes. Now, an important part is whenever you want to draw, you probably want to clear. Sometimes you want to clear the lines. For example, if I would, so this is just an example, I want to route this part right here. So it uses the clearance we defined in the style to clear around the trace. Sometimes if you don't want to use thermals, but you want to define your own shape, for example, having a trace, you go to mode, routing, and then new lines and arcs, clear polygons, MLC. Shortcut is MLC. If we remove it, and then we start drawing, we see that this new line here is now connected to this ground plane. It didn't clear the polygon. We don't want it, so let's go back, and now we press MLC, we see that it clears again the polygon. Let's undo it, and actually, so this way you could do some custom thermals if you're not happy with the thermals that exist, and you can connect to polygons or to planes. So let's continue the route. And there we have it. The routing is done. And if we look at the message Windows log, whenever we do CR, we see that the layout is complete and has no shorted nets. So we've routed all the parts. And I even managed to use 0 vias. Well, it is a pretty simple layout. It doesn't look too nice, but this is a rough routing. We will we will make it a bit cleaner afterwards. But it is possible to do the complete layout just in one side without vias. What we shouldn't forget to do is an outline to define the board size or the board shape. And you could use any trace here. Another important useful thing. What you see on the top right, on this corner here, you see the relative path. And for example, if I draw around here, the relative path, you see that if I go up and down, I can reach 0. It means that I'm on the same y-axis. I'm still 30 millimeters to the right, but I'm on the same y-axis. And this helps to route or to connect parts. This is always corresponding to the first marker. Whenever I click somewhere, you see that there is a cross mark, a crosshair, and this is the first marker, and everything you see in the corner is relative to this point. You can actually put markers yourself using AM. For example, if I want everything centered here, I just go in the middle, it snaps to this pad, I press AM, and you see there's a crosshair, and now my cursor is all of the time relative to this crosshair. This is a small trick to help routing and connecting things together, or at least aligning parts and traces. And to clear it, just press AM again. So now the outline is done. We should almost be finished. What we need to do before we export everything is do a DRC check. This is part of any good EDA software, and it is a good thing to do. First, we need to set up the DRC rules. You find them in the preferences under size DRC, go to DRC queries. And in DRC queries, you find there are plenty of DRC rules which you can check. You can disable them individually, but here, minimum copper clearance, it's set to 5 mils. I know that my manufacturer can have a 5 mil minimum copper clearance. 5 mil, and apply. And here the current value is 5 mil. Overlapping, it's the thickness of the trace which they need, which is 5 mil. Apply. Minimum drill size is 0.3 millimeters. We had all the hallways. The vias, which we didn't use in the end, has 0.4 millimeters, but the minimal drill size is 0.4. For hole, I don't know. Minimum copper thickness, this is also 5 mils. Apply. Minimum seal screen, I think it is 6 mils. 6 mils. And minimum ring is 0.2 millimeter. You just go to the capabilities of your manufacturer and grab the values from there. I'll say 0.2 millimeter. Now, once all the DRC values are set, you can actually run them. And here, for example, I run the DRC values and I have 0 violations. So it's not fun to have 0 violations. Let's try to make a violation and run it again so we can have an example of how it looks like. Let's have a line up, which is too close to the other line. These two should not be close, so this way. So here it doesn't contact, but it's too close. And normally if I run the DRC again, you can run individual rules by just selecting them and then click on run. And here we have 0 violations. If we want to run everything, do this here DRC check. So they will run all the checks which are still enabled. And now if we look at the violations, we see that we have 2 close tracks which are too close, and these are the tracks which I've just created. So let's remove them, remove, and run again, refresh. Then we have 0 violations. And now we're almost done. The last part is now rendering everything. So we want to export this as a Gerber and drill file, excellent drill file, so we can send it to the manufacturer. And this is done in export with CAD job. So let's export the CAD job, and we see we have plenty of CAD rules because there is no standard way to name the files. Every manufacturer has some preferred files, and we can see that in the digest we have all the Gerbers, and then we also have the fabrication file and the Epsilon drill file. And if we want the Gerbers, we just click on export, and then it complains about some things because there are some parts we don't have. For example, we don't have anything on the bottom assembly, so it will tell there's nothing to export. There are no objects within this layer, so it's fine to not export them. The rest of the files have been exported, and we can have a look at them. Here we are in the folder. We see that we have this LHG file, but we also have all the GB, top, bottom, and so on. You can now send the file to the manufacturer and get your PCB. But these are just the basics. pcb-rnd is very powerful, and there are a lot of things which I didn't show yet. But these are advanced topics I might show in other videos. But there's one last part I want to show which is quite good with pcb-rnd, is that you might not know how to do certain things because they're a bit different. And for that, on the top right, you see that there's online support. If you click on it, and I'll the demo user, just put your name on it, it will connect to this IRC channel, which is a live chat. And once you are connected, you can actually talk to the developers and the other users of pcb-rnd. And they're very friendly and always helpful. And I use them very often, even to report bugs. So let's say hi. They react really fast, and this is also why I like this project. But now it's up to you to test pcb-rnd and see if it matches your taste. Enjoy!